Good morning. Hope you're doing well. Beautiful outside, though a little bit cold. So we're going to do some more Lenz's law. These things, there's a lot of them, and it's pretty important on this exam. It's weighted fairly heavily, so it's good to have a good solid understanding of kind of the flow that these problems have. So yeah, let's get started. Hope your day has gone well. Mine has gone great so far. The figure above shows a circular loop of area 0.25 meters squared and a resistance of 12 ohms that lies in the plane of the page. Magnetic field of magnitude B directed into the page exists in the area of the loop. The field varies with time t as shown in the graph above. Okay, so we got a loop, circular, check. Into the page, magnetic field, also check. And we have a graph of said B field. Okay. Focus. Don't panic. Try not to panic. Whew. Okay. Derive an expression for the magnitude of the induced EMF in the loop as a function of time for the interval. Man. At some point, so many words just kind of go through. It's easy to just kind of Okay. So we have induced EMF, we have magnitude, which means the negative sign, though it's good to understand, will not be needed for this part of the problem. Function of time, t equals 0 to 8. So this section right here. Okay? So induced EMF is, use Lenz's law. Now, my first epsilon of the day is always terrible. Negative d flux dt equals, scooch over a little bit, d dt, don't forget the negative, of magnetic field times area, which equals negative d dt b times a. I'll just distribute the negative, b times dA dt. We know that the area of the loop is constant, so the change in area with respect to time will be 0. So we're left with this portion. Back to blue. We know that the magnetic field for that section is 1.8 times E. I'm going to write that as negative 1 over 20 because 0.05 is just 1/20th. It might make it easier later with the derivatives and the such. Times the area of the loop, which is, I'm just going to write that as A for area because we know that it is 0.25 square meters. Okay? So taking the derivative here, so we have 1.8. I'm going to call 0.25 meters squared 1/4. And then we're going to do E to the, so an expression for the magnitude as a function of time. Okay. So we can still have E involved. And then we're going to, should be a negative here. We can really ditch the negative because it's magnitude, but I'll leave it. And then we're doing the, what's it called? The chain rule? The chain rule, where we take the, for E, we take the derivative. So the derivative of E to something will be E to the something times the derivative of the something up here, which will be negative 1 over 20. Okay, rewriting this one more time. We'll have plus, plus. Let's go over to Wolfram. And we'll do 1.8 divided by 80. And that's 0.0225. I don't like 0.0225. I was hoping for something a little bit cleaner. Oh. So this will be the induced EMF for the loop based on the changing magnetic field. Okay, derive an expression, magnitude, induced EMF in the loop as a function of time for the interval t equals 0 for t equals 8. Okay, and just to be for 0 less than t less than 8. Yeah, that seems reasonable. Okay, so we're good there. And then, yep, just for good measure, we'll put in a V for volts. Okay, on to A2 to the lies. Calculate the magnitude of the induced current in the loop at t equals 4 seconds. Okay, so current equals V over R, which equals, in this case, I'll make a little arrow because it's not necessarily really equals. This is the general idea of a current. This is going to be the current for the one that we're looking for. Nope, didn't mean to throw in a random negative sign. There we go. So we need to find this value of t at 4. So we have 0.0225 e to the negative 4 over 20, which is 1/5. Yeah. Over. And then we got 12. Okay, and we go back over to Wolfram. I'm going to simplify this slightly. So this is negative 1/5, which equals negative 0.2. There we go. So let's see, 0.225 e to the 12th. So here we go. Times e to the negative 0.2 divided by 12. Is that right? I'll click enter and just see what happens. And so we get, wow. So we have 1, 2, 3. So 1.54 milliamps. 1.54 milliamps. All right, so remember that? Remember that? Equals 1.54 milliamps. Yep, that seems reasonable. 1.4, it's not a lot of amps. It's okay, it's an induced EMF. Induced EMFs are generally small. Maybe. Yes, so that's the correct answer. Let's go on to, let's grab the next problem. I guess the next part of the same problem. The B. Kind of awkward to have an A without a B. Probably should clean the board up a little bit too. So clean this up. Okay. So we have our next part. Sketch a graph of the induced current I in the loop as a function of time from t equals 0 to t equals 18. Okay, so just this section right here on the axis below. Oh no, from to 18 all the way out to here. That's just 8. Okay, assuming that a counterclockwise current is positive, and they label counterclockwise and clockwise is positive. Okay, so this is going to be the actual analysis part. Well, the thinking portion. I guess they're both thinking portions. So we want to start by finding the direction of current, which is all that we really need to find because we already found the magnitude. So Lenz's law is electromagnetic force equals negative d flux dt. So we have a flux original going into the page. This flux is going to go down. Therefore, by Lenz's law, a flux is going to be created that compensates for this drop. And so it's going to raise the flux, which will cause a rise in current in the same direction as the current magnetic field. So the magnetic field is into the board. So you do a right-hand rule. And to create a magnetic field, put your fingers along the loop and your thumb points in the direction of the magnetic field. So you'll have a current that's going clockwise. It will rise in the clockwise direction. So we have a clockwise current. Okay? And the current will be proportional. I'll do a little proportional sign will be proportional to current. So I equals V over R. R is a constant. So the induced EMF will be proportional to the current. So we can basically just draw the what the EMF will look like, and that will give us something that's proportional current, because we don't have to be exact here. We're just kind of sketching it out. So we know clockwise, so we're going to be on the bottom, and we're going to be clockwise as long as it's going down. So it looks like it's going down the whole time except for right here, where it's just flatlining. And this part here is exponential, and so the EMF, and therefore the current, will be proportional to the derivative of that. So the derivative of an exponential is an exponential. So we'll start by drawing, zoom in. I've been leaning on blue a lot. I like blue. Okay, so the exponential goes to what? 8? 8. So we'll do exponential, and then it flat lines, so the derivative of a constant is 0. So since the magnetic field and area of the loop are constant, that will produce 0 EMF. And then it drops linearly. So there is an M here for a slope. And then when we take the derivative of that, that will give us our EMF. We'd have to, in the EMF, we'd have to take divided by current. We're not doing exact numbers here. So we're just going to say then that it is constant. So I'm going to write constant with a little arrow, and I'll write exponential with another little arrow. And, oh, then it gets to 16, 12 to 16. There we go. And then at 18, it's 0. So, got a little carried away there. Oh, no, I realized. So much harder than I initially expected. There we go. So that's the correct graph. For the time interval, 12 to 16, justify the direction of the current you have indicated on the graph. Oh, so basically what we just did. Okay. So for this, I will say, for the time interval 12 to 16, justify the direction of the current you have indicated in your graph. So I would say flux original lowers, therefore flux induced rises, therefore magnetic field induced rises, therefore current has to be clockwise. For the time interval, justify the direction of the current you have indicated in your graph. Okay, so when I answer this question, I'd start by just writing this out. If you have enough time, I'd just write that out. And if you're stressed for time, I'd just move on. If you have a little bit more time, I'd write it out in words then, basically explaining the original flux lowered, therefore that was compensated by the induced flux rising, which would cause a rise in the magnetic field, which would require a current in a clockwise direction. So, which is the same thing as what I wrote here, but you might want to write it out in words to make the person grading it feel that you understand the knowledge. So, I'm always kind of justify the direction, because it's one of those things where you can ask a really simple question and expect a really simple answer, but there are some complicated underpinnings in life that you can really go into the weeds. So try not to get too bogged down with the justify part. So this is, I feel this would be sufficient. It's one of those things you never know what's sufficient until it's actually graded. But if you want to do more than this, and then just write out the exact same thing you just wrote, but in words. Write out the same thing you just wrote, but in words. I don't know if that's deep or just dumb. Oh well, I'll keep saying it as if it is deep. Calculate the total energy dissipated in the loop during the first 8 seconds as shown. Okay, so now this is power. What? Power. Yeesh. One of the mnemonics that I like is centripetal acceleration equals electrical power. And the way I justify that is centripetal acceleration is v squared over r, and power is also v squared over r. Except this is voltage over resistance, and this is velocity over radius. So, but I like to write this just because it's such a terrible gross conceptual error that it's a great mnemonic. Because, now granted, centripetal acceleration has always been easy for me to remember, and so has power for v squared over r. But if you're having trouble remembering one but not the other, this is a great mnemonic because it is such a blazingly flashing red light mistake that it's just easy to remember. You always remember the red flashing lights. So power is voltage squared over resistance. So that is where we are going to start. Pull up the sleeves. That's how you know I'm getting serious. Mostly serious. You should never be too serious in life. I don't know. How serious should you be in life? I think you should work hard and do your best, but at the end of the day, not worry too much. Which is much easier said than done. Alright, so power equals voltage squared over resistance. We have then induced EMF squared over resistance. We have a equation with respect to T for voltage squared. So we have .0.0225 e to the negative 1/20th T and then since it's changing over time, we're going to have to, first we're going to have to square this, and then we're going to have to do the integral from 0 to 8. And 8 is the exponential portion right there. And then we're going to divide by r, which is a constant. So first thing I'm going to do is I'm going to pull out as many constants as I can. So we got this induced EMF by taking a derivative. So I kind of feel that there's probably some way of, instead of taking a derivative and then integrating back to get the original, there's probably some way to kind of skip that step and make it simpler. But I'm not sure, and it would take me too long to figure it out. So since I already have the integral here, and that square might mess it up. So for what I would do here is I would just, we already have the integral, or we already have the derivative, which is the EMF. We'll just integrate it back again. So there might be some time-saving issue there. Not worth finding. Okay, so let's do the 0.0225 divided by the resistance. So we have 0.0025, which I think is that, divided by 12. We'll get an even smaller number. So we'll do 1.875 times 10 to the negative third. Okay? 1.875 times 10 to the negative third. Ooh. Grab a drink real fast. Delicious purple. Purple is probably my favorite flavor. Alright, so I got 0 to 8. E. Now, this e to negative 1/20th squared, this 2 can then just multiply by the 1, and so you have negative 1/10. Yep. dt. And I'm pretty sure this is just negative 10 times to the e, but I am terrible with these sort of things. So what I'm going to do is I am going to actually work this out. If I was on a test and I was just rushing through this, I'd probably be like, that's probably negative 10 times e to the negative 1/10 t. But I don't know. U equals negative 1 over 10 t. du equals negative 1 over 10 dt. Negative 10 du equals dt. Therefore, this is the integral of e to the u times negative 10 du, which is e to the u times negative 10, which is negative 10 times e to the negative 1/10 t. Okay, so I was right, which is negative 1.875 times 10 to the negative second. I just took the 10 and moved it over. And then we have, do a little parentheses here, e to the negative 1/10. And I will do 0 to 8. So I took that negative and just flipped the limits of integration. 0 to 10, which is 1.875 times 10 to the negative second. And then this will be 1 minus e to the 0.8 negative. Okay, it seems reasonable. Maybe. Let's Wolfram this. 1.875, so I'll multiply by 10. This gives 1.875 times 10 to the negative. I know, I'm kind of cheating with Wolfram because you really can't do this with your calculator. So I should be using the calculator and the clickety. Nah. I trust you guys. 1 minus e to the negative 0.8. Let's see how Wolfram says on that. I know Wolfram just gives me the answer and I click it anyway, and I should. It's fine. I like to see the equation here to make sure I got something kind of sort of correct. Okay. Seems. I think there should be something squared in there. Let's go back over. So I think, yeah, maybe I forgot to square that. So I'm just going to redo this constant again. So this constant is 0.0225 squared over 12 times 10. So this would be 1.2. And then the negative switched the image. Yeah, let's try that. 0.0225. Okay. Maybe. Go back here. So we'll do 0.0225. Is it 0.0225? 0.0225, yep. Squared divided by 1.2. That looks more, yes. I'm good with that. Okay, so this will be 2.32 times 10 to the 1, 2, 3, 4. 2.32 equals 2.32 times 10 to the negative 4th joules. Whoop. Calculate the total energy dissipated and looped in the first 8 seconds. Okay. I think that would have been less work if I made fewer mistakes. Which is kind of funny too. It seems a lot of times in life that not making mistakes is often the biggest part. At least avoiding big mistakes. Because you're going to make a lot of mistakes in life. There's a phrase that smooth is fast, fast is smooth. And the idea is if you focus on good technique and not making major mistakes, then life will go smoother. So the mistake I should have avoided there was forgetting to square. That when I squared it, I forgot to square the constant. So 2.32 times 10 to the negative 4th joules. That's a J, just in case you had trouble seeing. So it took me about 25 minutes or so. I think if I'd been pushing faster, I could have gotten done in about 15. You need to get about between a 60 and 70%. Your goal should be about 60 to 70% on the test. I think a lot of universities will take a 3 on the AP exam, so you can do a little bit less. But you should always aim for 1 higher. If your minimum score you need is a 3, you should aim for a 4. That way when you fail to get your 4, maybe you get a 3, then you're still okay. Because there's going to be some standard deviation in the bell curve of your performance. So you want to take that into account. There's no way you can guarantee you'll pass a test, even if you're brilliant. But you can raise that to a fairly high percentage. Okay, so I am going to clean up the board, and we will try another problem. There's an amazing number of Lenz's law problems. This could legitimately be a quarter to a third of your test overall, is these kind of magnetic induction problems, especially in the free response section. So it's worth knowing how to do these. Unlock, delete, clean up, grab the next problem. There we go. I like how the last problem had like A, B, and C on 2 separate pages, and this one has all the way through E on just 1 page. How much more efficient is that? But the other one had like subsections to the problem, so I'm never quite sure how you count how many problems there were. When it's like, well, whatever, it's fine. I'll get over it, don't worry. Okay. So, I'm going to need a drink before I do this problem. I don't know if you're allowed to have drinks during the AP exam. Probably not. You only have, it's like only an hour and a half test too. It's crazy. So you have 45 minutes for multiple choice and then 45 minutes for free response. It's like, that's a lot of writing. And ideally, you'd take the mechanics physics in your junior year, but almost no one knows to even study for that your junior year. So most people, when they do mechanics physics, they do it in their senior year, and they barely kind of sort of touch on the electromagnetic their senior year of high school, and completely not enough to take the test. So ideally, your junior year, you would take the mechanical, and then your senior year, you'd take the electromechanical. But then you want to take the calculus test, which is the BC, calculus BC, before or with the physics test. So really, you should be studying for the calculus AP exam your junior year of high school. I don't know. It's a lot of work. I don't know if you can because you always have like that one guy that like didn't graduate on time, so he's like a year older than everyone, like a super senior, if you will. I wonder if you can intentionally do that just to pass AP exams your whole extra year. So your goal would then be to basically do your freshman year of college while in high school, but you do an extra year of high school just to study and do AP exams. I'm pretty sure that's frowned upon. I would not do that as your goal, but if some guy was trying to play the system and be a jerk, man, I'd almost be fine with that. I would almost think like, good for him. Or her. Yeah, it definitely sounds like the sort of thing a man would do, though. I doubt a woman would be that much, or girls generally aren't as rambunctious and countercultural and just being a jerk in life. Okay. Back to the problems. So, okay. I see where this is going. In the diagram above, a nichrome. I assume that's nickel chromium. That's probably I think that's heating wire, like resistor toaster. Nickel chromium, chrome nickel. Is any of various nickel alloys and often iron. A few other applications. Resistance wire. Ooh, also dental fillings. Uses. Almost any conductive wire, but most metal conduct with great efficiency, requiring them to be formed into very thin, delicate wires. Ah, so it's a slightly less competent electric ignition systems, model rocket igniters. Ooh, I think they're also used in like those vaporizer things, the electronic cigarettes that the kids are doing nowadays. I don't know if the kids are doing it or if it's just a hipster thing. I don't know. All right, you should not have this deep of philosophical thought while you're trying to take the exam. Nichrome wire resistance per unit length lambda is bent at points P and Q. Check, check. So it's all one wire, it's just bent. They didn't like solder it together or anything. Or weld it? Do you weld nichrome wire to form horizontal conducting rails that are a distance L apart? Okay. The wire is placed within a uniform magnetic field of magnitude B, pointing into the page. A conducting rod of negligible resistance, which was aligned with ends P and Q, check, check, at time t equals 0, slides to the right at constant speed V, and negligible friction. Okay? Express all algebraic answers in terms of the given quantities and fundamental constants. Indicate the direction of current induced in the circuit. Ooh, ooh, ooh. Okay, conducting rod, which is aligned, slides to the right with constant speed and negligible friction. Okay, so I think this is a railgun. Let me... Railgun? Do they have a schematic? Schematic! Show me a schematic! Demand schematic! Maybe that was it up there. I'll click in a sec. No, 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 no. Ah, you're killing me. Wow, they got a lot of info on this. They are sweet. Yep, so right here. So you got your two parallel wires, you got your sliding thing, you got the velocity. And so the idea here is... Ooh, German. You know it's well built in. Okay. So the idea here with a railgun is you have a current, and that current forces all the wires to pull apart. Well, if these three are stationary and this one is not, then that shoots it off that direction. And I think they have something called like a sabot normally, sabot, where basically it's like a enclosure for the bullet, so that once it gets out of the barrel, then the hard metal bullet part still flies. And that way the sabot is just, sabot? I should figure that out. It fits into the barrel well and flies out. But this is different. They don't have the, instead of putting an electrical current through the wires, they are forcing, using some sort of external force to pull this bar at a constant velocity. And that pulling of the bar is going to create the current. So instead of creating motion from electricity, they're creating electricity from motion. Okay. So indicate the direction of current induced in the circuit. Okay. So I am going to write up Lenz's law real quick. E equals negative d flux dt, which equals negative, and this will be dB dt times area plus B dA dt. Okay. Green. So we have a uniform magnetic field. I assume they say that. Uniform. Which means that dB dt equals 0. But this portion right here is not 0. We have a magnetic field times area times T. So we have negative B dA dt. And so we have a magnetic flux original, which is getting bigger. So magnetic flux is getting bigger because the magnetic field is constant, but the area is getting bigger. I think in our previous problems, we've always had the magnetic flux go down. But now our magnetic flux is actually going up. Not because the magnetic field is getting bigger, but because the area that is covered is getting bigger. And so to compensate for this, the flux induced will oppose the field, and therefore the magnetic field will go down because it has no choice in the area. Therefore the current, so we have the magnetic field into the board, so we're going to create a magnetic field out of the board. And so wrap your fingers around the direction of the wire, and your thumb will point in the direction of the magnetic field. And so it's going to create a magnetic field outward, and so the current will be counterclockwise. Whoop, counterclockwise. Okay, that's a lot of thinking for whoop, whoop. And to justify it then, I would just write this out right here. Original flux goes up, flux induced goes down, therefore the magnetic field induced will go down, therefore the current has to be counterclockwise to create that magnetic field going down. And by down, I mean opposition, opposes the direction of the original magnetic field. Derive an expression for the magnitude of the induced current as a function of time. Ooh, ooh, ooh. That seems like a lot of work. Okay, so now that we have this knowledge of the direction of current, I will erase it. We already have it written up on the diagram, so we're good with that. Click, clack. So it's basically saying, solve this. It's like, that's a lot. Okay, so we're up to this point, negative b dA dt, which equals, so we want to first find the induced EMF, the voltage, and then we will use that to find the current, which will be interesting because as the square gets bigger, the sides of the square get bigger, rectangle, sides of the rectangle get bigger, and that will cause greater resistance. So negative b, now we're taking the derivative with respect to t of length times width, which is negative b times, we'll use the product rule, d dt times L times W plus L times change in width with respect to time. Okay, and I'm saying that this will be length and this is width. So the width across the bar does not change with respect to time. L does not change, that's a constant. But width will, because it's moving. So wires place uniform magnetic field. I'm just trying to see where the bar is. Do we have an initial width? The T slides to the right with constant. That's okay. I don't think it matters. So, whoop. So the change in length of the bar with respect to time will be 0. So this term will be 0. And we're left with negative b times L. And then the change in width with respect to time is actually v for velocity. So I'll draw a little arrow here, not really to show that it's a vector, but to show that it's not voltage. Yeah, it's an abusive notation, but it helps me keep it straight. And this is E. So in the military, we had a mnemonic for this, and the mnemonic was, everybody loves velvet bunnies. So the idea was E, induced EMF, L for length, velocity for velvet, and B, which is the magnetic field. Everybody loves velvet bunnies. So the induced EMF due to a sliding bar is everybody loves velvet bunnies. And this is the derivation for it, but it's also good to kind of know the answer too, because that way if you don't get the answer, you can go back and figure out where your mistake was. Okay, so we got the induced EMF. Express all algebraic in terms of given quantities, just all your ends right. Induced current as a function of time. So, yep, okay. So current equals V over R, which equals E over R, I'm going to say of T here. So the resistance will be, so we'll have negative magnetic field, well, negative, everybody loves velvet bunnies. And the resistance will be, we have a lambda, right? So lambda is measured in, so it's a small amount of resistance for a small amount of length. So lambda equals, so resistance equals lambda times length, where length in this section is actually going to be the velocity, the speed, times time. So that's how far the bar has traveled. So as the bar is traveling, it's going to be picking up more and more resistance. So we're going to have the resistance due to the bar. So we have this bar, 2 times length times lambda, plus 2 times, let's see here, we do velocity times time. That'll give us the width times lambda. And the idea here, the reason we have the 2 is because you have to go forwards and backwards. So I'm going to simplify this a little bit. And we're going to say current equals, ooh, that's a lot of values. Lambda, velocity, magnetic field, 2 times a lambda times L plus VT. Yep, and I just dropped the negative sign because we know the direction. Derive an expression for the magnitude of the induced current time. Okay, so this will be the induced current for a given time. And the reason the bottom is so complicated is because the further the bar goes, the more resistance it's going to pick up, because the resistance is a function of the wire length and not just, hey, here's a resistor. Okay, take a look at this real quick, make sure it didn't go too crazy. Magnetic field. Ooh. Negligible. Okay, I'm going to revise my answer slightly. I'm going to clean up the board. Whoop, whoop. So the idea is that the conducting rod that we had was not made of nichrome. And so this 2 lambda L I had, it should not be 2 lambda L. It should only be 1. So I'm going to rewrite that as, can I do that? Yes. Yes, I can. Equals L VB over lambda times L plus 2V. Yep, I'm good with that. And so I basically just took out one of the widths because we can't assume that the conducting rod, which is of negligible resistance, has the same resistance as lambda. So, do I have an expression of magnitude of the current? Okay, bam. I hope that was the hard part of the question. Do I have an expression for the magnitude of the magnetic force on the rod as a function of time? Okay? We can do that. So the idea here, we can probably get rid of these. Maybe. Yeah, I'm sure we're fine. Cleaning this up. So the idea that we have here to find the magnetic force comes down to our equation F equals QE plus QV cross B, where we assume the electric force is 0, and so we're left with QV cross B, and this would be force due to magnetism. And I would just jump straight to the equation. So the way one mnemonic to know this is velocity is measured in meters per second, while Q is measured in coulombs. And so if you take this 1 over seconds and move it over to the coulombs, you're left with coulombs per second times distance cross B. And when you're measuring, I know it should be Q per T, that's fine. Coulombs per second is amps. And so what we have here is force magnetic on a wire is IL cross B. Now, the way in the military that this mnemonic is remembered is fire incinerates little bunnies. I know, it's very childish. If you think about people in the military doing technical engineering things, think of it like 15-year-olds playing with transistors and such. They're they're very serious about doing their job, but they're also, basically like little boys. And so some of their mnemonics reflect that. So the mnemonic used is fire incinerates little bunnies, which goes well with everybody loves velvet bunnies. So fire incinerates little bunnies, FIL cross B. So we're going to use this equation here. And since you look at L cross B, L is the direction that the current is flowing through the conducting rod. L cross B, F equals L cross B, okay? And so it's actually going to be creating a force to the left. The induced force. Function of time, okay? And L and B are perpendicular, so their cross product will be 1, since cross products are sine. So we will have I, which we've already discovered. So we have LVB over lambda L plus 2VT times L times B. So it could be L squared plus B squared. So maybe if I just yep, there we go. And that is our force magnetic due to time. And I'll erase this portion and keep this because it may be useful later. Find something useful and then I erase it. Such is the story of my life. Okay. So we got the current, we have the force. On the axis below, sketch a graph of the external force as a function of time that must be applied to the rod to keep it moving at a constant speed while in the field. Label the values of any intercepts. Okay. So what it's saying is we already saw up here F equals Q V cross B, or F equals I L cross B, will produce a force to the left, because L cross B, or V cross B, which you're looking at the positive charges moving in the positive direction, will create a force to the left. So there's some external force to the right that has to be applied here. This is what it's talking about, this external, F external. And so the F external, for a constant speed, the acceleration equals 0, force equals mass times acceleration, so the external force has to equal the induced force. So what we're basically going to do is just graph the induced force and be like, here's your external force. And so we have force up here, and then we have time on this axis. So we're just going to look at this equation as time goes to big. So I'm just going to go to Wolfram real quick. Not going to graph the whole thing, but y equals 1 over x. Because we have x in the bottom, and so we're going to get something that looks kind of like this, where it has the 1 over x. But we're also going to have, I'm going to find fb of 0, where 0 is for the t, and that's just going to be L squared v b squared over lambda L, because the 2vt goes to 0, one of the L's cancels, or LV b squared over lambda. So what we're going to have then is something that looks like this. Actually, I could just use a real line. I could draw. So I'm going to start here and there, concave down. Ooh, that looks surprisingly competent. I'm good with that. And then we'll have the intercept, which will be LVB squared over lambda, right there. Yep. The force pulling the rod is now removed. The external force is removed. Indicate where the speed of the rod increases, decreases, or remains the same. So, decreases? So what's happening here is they're saying we have maybe they're trying to give you easy points here, and it's one of those things where when they give you a present, you're always skeptical, and so it's hard to accept a easy question. So we have a force induced to the left. We have a force external to the right that allows us to maintain this constant speed. And so if we remove this force to the right, we'll be left with a force to the left. And what that force induced will do is it will reduce the speed. Yep, it'll reduce the speed. And it'll never actually stop because we're assuming frictionless here. But it'll keep slowing down until it asymptotes out at stopping. So if the external force is removed, we won't have anything to counteract the induced force, and therefore the induced force will cause the rod to decrease. And I would just write that out. Force external equals force induced. Therefore, if force external is removed, the force induced will slow the rod. Maybe you should say conducting rod. Whoa. There you go. I'm good with that. All right. So that's how you do this railgun type. Reverse railgun? I'm not sure. Generator? Because you're basically generating. This is like a generator where you pull it. Anyway, the idea here is you'll see this sort of sliding rod thing time and time again, and this is the way you approach it. Normally I haven't seen where the wire has a innate conductivity to it, so that's kind of cool. Normally you just see like a small resistor and they're like, yep, all the resistance in the whole system is just there. So that's a little bit different than I see, but you'll see this come up again and again. The two mnemonics that are useful to know here is everybody loves velvet bunnies. I think that's a cross product there actually. And then fire incinerates little bunnies. Small bunnies. Fire incinerates little bunnies, which is just a rewriting of QV cross B. Okay, sounds good. We'll probably do a few more Lenz's laws, and then that'll kind of round out what you need to know for the physics exam. Thanks for joining me. I will see you next time.